Finite automata. Finite automata is a mathematical model or a diagram that represents or recognizes the regular languages or the type tree languages which we have read earlier. So the finite automata is a diagram which will recognize a regular language. That means it is of two types. Either it will give the output or it won't give. When it won't give the output, then it is a language recognizer. That is, we can, if we reach a final state, then we come to know that the language is valid. If we do not reach the final state, then it is an invalid language. And the one with output capability is known as the output generators. That means it will generate some output for a given input. Here it will check for the language, and here it will generate the output. So the output generators are of two types, Moore machine and Milli machine. And the language recognizers, these are of three types: DFA or deterministic finite automata, non-deterministic finite automata or NFA, and epsilon NFA. Deterministic finite automata means here we will get for a particular input, we will get a determined answer whether it belongs to or does not belongs to the language. For non-deterministic or NFA, here it won't be a definite way. And epsilon NFA, the NFAs that include epsilon as an input symbol are the epsilon NFA. So specifications of finite automata, we have here 5 tuples. M equals to Q, sigma, del, S and F. M is the mathematical model or the finite automata. This is for the finite automata as a whole in general. Finite automata. Later we will get to know about DFA, NFA and all in particular. M is the finite automata. Q is the set of the states or phases. In our mathematical model, we will transfer from we will do transition from one state to another. So Q is the set of states. Then sigma, as we had read earlier, it is the alphabet or the set of input symbols. Then del, this is the transition function, that is the relation of the input with output. This function or transition table will relate the input with the output, input symbols with the output states or symbols, output states in case of DFA. Then transition function is different for different types of language recognizers. Then S is the initial state, and it is only one because we can only start from one state. Then is the final set, the set of final states, or F, that will include the all the final states that we have. So F is a subset or equal to the set Q, and S is the element of Q. And we have 5 parameters for the finite automata. For a DFA, the transition function, it is a subset, it is a function from the product of Q and sigma to Q. That means the function output is a state and the function's input will be the state along with input. We will see the table. Then comes the diagrammatic representation of DFA. So this is how a DFA, simple DFA looks like. We have here some circles and then arrows and the numbers. Here the circles are the states. The states are represented by circles and they have the name or labels S1, S2, S3. Then we have the arrows. The transitions from one state to other is represented by an arrow with a input label with it. Here inputs are 0 and 1. We can see only the symbols 0 and 1. These are the labels. and this arrow is empty because this indicates that this state S1 is the start state. So we will start from here. If we get 0, then we stay in the state S1. If we get input as 1, then uh, we do the transition from S1 to S2. For example, if our input string is 1101, let us see if this string is valid or not. Well, this string will be valid if we reach the final state. This string will not be valid if we reach in some other state. 1101. So my first input is 1. I will start from the state S1 because this arrow indicates this is the initial state. So on getting 1 as input, I do the transition from S1 to S2. So I reach here, then again I get 1, again I'll get 1, then I'll stay at the same state S2, then comes 0. On getting 0, I am going to the final state S3, but since my string is not complete, I have to check for the rest of the bits, that is 1. On getting 1, again I am in S3. At the end of the input string, I have reached the final state. Therefore, this string is valid for this DFA. And for DFA, for each state, we should check for each input symbol. Like for S1, we have the transitions for both 0 and 1. For S2, 0 and 1. For S3, 0 and 1. If any of the transition is missing, like here I have not given for 1, this thing is not there, then it is a invalid DFA or it becomes a NFA. For DFA, we should exactly have one transition for each input symbol from one state to another. Then the functional representation of this diagram. Here Q means the set of states, that is S1, S2, S3. Then sigma is the input symbols or alphabet, that is 0 and 1. Then S is S1 because this is my initial state depicted by the arrow. F is the final state depicted by double circle. We will always depict the final state by double circle, and it is a single element. So my transition function, if for this function, if S1 and 0 is the input, S1 and 0 is the input, I'll get S1 as the output. Because for transition function, we will take both state and input and we will get state as output. So for, and again for del of S1 comma 1, for 0 we have seen here, for here we will see for 1, it is S2. 1 for 1, it is S2. Similarly, for all the functions, for all the states we have done, for S2 comma 0 it is S3, S2 comma 0 it is S3, and S2 comma 1 it is S2. Similarly, representing this data into a table format, we can have this side as the input symbols 0, 1 and so on, and here we will list the states. Final state is represented by a star and the initial state is represented by this arrow. So S1 with 0 is S1, S1 with 0 is S1, and similarly this table is filled. Let us see a question. Construct a minimal DFA that accepts all strings of A's and B's including epsilon. Okay, so construct a minimal DFA. Minimal DFA means DFA with minimum states that accepts all strings of A's and B's. Here A and B is our sigma, that is the input symbols, and then it must include epsilon, that is strings of 0 length should also be included. So my language becomes epsilon 0 length string, then 1 length string, 2 length strings, and then 3 and 4 and so on. So I have to make a DFA that will accept epsilon. So whenever I'll start the transition, it should reach the final state. That means my start state is equal to final state. It is accepting a epsilon. So I have to make the start state as final state. Like S1 start state represented by the arrow is S1, and S1 is the final state represented by the double circle, and then whatever I'll get input, whether it is A or B, I'll remain at the same final state S1. So S1 double circle AB. Then next question, construct a minimal DFA that accepts all non-empty strings. Non-empty strings means no epsilon is not included, of A's and B's. Similar as the previous, sigma A comma B, then language, we do not include here epsilon, and then the rest of it is the valid language. So here my start state is not equal to final state because I am not accepting here epsilon. So at least one is needed, A or B. So we make a start state S1, and for any input, whether it is A or B, it will reach a final state S2. And after that, whatever will come, that is also included as the final state. So I will remain in the same final state S2. Okay. So, and the transition for this transition function, S1 on getting A, it is S2. S1 on getting B, it is S2. S2 on getting A, it is again S2, and S2 with B is again S2. Thank you.